In this example, we're going to start with a basis of R2. That basis will be comprised of the vectors 3, 4, and 2, 0. We're going to apply the Gram-Schmidt process to turn B into an orthonormal basis of R2. Now, given that we're already starting with a basis, we simply need to go through the two steps to turn it into an orthonormal basis. Now, for the sake of simplicity, we're going to refer to the first vector in this set as v1 and the second vector as v2. Our first goal is going to be to create an orthogonal basis that we're going to refer to as b prime. That will consist of vectors w1 and w2. The idea is every time we create a new vector for basis b prime, it has to be orthogonal to everything that's already in basis b prime. So with that in mind, to create the first vector, there are no other vectors already in the basis, so there's nothing else to do other than just grab that vector. However, every time we add a vector beyond the first vector, we're going to be subtracting orthogonal projections in order to create vectors that are orthogonal to the vectors that are already within the set. Let me give you a symbolic representation of what I mean. To create w2, we'll take the vector v2, and we are going to subtract the orthogonal projection of v2 onto w1. The process of subtracting this projection creates a vector that is orthogonal to the vector that's already in the set. So we take the vector v2, which is 2, 0, and we are going to subtract the projection of v2 onto w1. The formula that we have for this is the dot product of v2 with v1 divided by the dot product of w1 with w1, that should be a comma, not a dot, multiplied by the vector w1. So this is v2 minus v2 dotted with w1 divided by w1 dotted with w1 times w1. Probably should have copied this part down first because that's the formula that we're using. Now, to actually evaluate all of these things, we'll perform the products first. Minus. So this will be 2 times 3 plus 0 times 4. 2 times 3 will give us 6. 3 times 3 and 4 times 4 is 9 plus 16. That'll be 25. Multiplied by the vector 3, 4. Wow, that fraction was unnecessarily large, wasn't it? So 2, 0 minus, once we distribute the 6 25ths through, we'll be looking at 18 25ths, comma, 24 25ths. Now if we were to get a common denominator, of course, this would be 50 25ths minus 18 25ths. That'll be 32 25ths. 0 minus 24 25ths won't take too much time or effort. Now, for the sake of simplicity, what you might do is, at this point, consider taking out a common factor to the two components. What I'm seeing is that they do have a common 8 25ths that we could pull out. If we do pull out 8 25ths, we'll be left with 4 for the first component and negative 3 for the second component. This process of taking out the 8 25ths is really going to be beneficial when we're creating b double prime. Now, if we were to use the 4 common negative 3 and the 3, 4 that we started with, a quick dot product will give us 12 minus 12, which verifies that these two vectors are in fact orthogonal to one another. So b prime being equal to the vectors 3, 4, and you can write it in either fashion, 32 25ths, comma, negative 24 25ths. This is now an orthogonal basis. To create an orthonormal basis, we need simply divide each of these vectors by its own magnitude. We're going to refer to those two vectors as u1 and u2. So this will be vector w1 divided by the magnitude of w1. So the vector 3, 4 divided by the square root of 3 squared plus 4 squared. Hopefully we recognize from right triangle trigonometry that this is simply the 3, 4, 5 right triangle. Now when we go to do this process, though we could technically do this with the 8/25 already in there, we could also factor it out of each of the things that we're about to calculate. So W2 divided by the magnitude of W2, this is going to be 8/25 of 4 negative 3 divided by, when we go to take this magnitude, the 8/25 will already be able to be factored out. Then we'll simply be doing 4 squared plus negative 3 squared. The 8/25 will wind up canceling out to give us a much more nice calculation. 4/5, negative 3/5. As such, our orthonormal basis, B double prime, since we're just about out of room here, will be the vectors 3/5, 4/5, and 4/5, negative 3/5, parentheses, set brackets, yeah, it totally fits, kind of. This would be considered an orthonormal basis of R2. Cool, totally made it fit.